We're about to embark on a journey into one of the universe's deepest mysteries, something so elusive that it makes up most of our cosmos, yet we can't see it, can't touch it, can't even directly detect it. Tonight, we're diving into the enigma of dark matter. I'd love to know where you're listening from tonight. Drop your time and location in the comments below. Are you watching the stars emerge in your corner of the world? Perhaps it's morning where you are, with sunlight streaming through your window. There's something beautifully fitting about discussing the invisible universe while we're all scattered across this small blue planet, each of us experiencing this moment under the same vast canopy of space. Imagine for a moment that you're standing in your backyard on a clear night, gazing up at the Milky Way stretching across the darkness. Every point of light you see, every star twinkling in that cosmic river, represents something extraordinary. But here's what will absolutely blow your mind. Everything you can see up there, every star, every galaxy, every nebula glowing in the distance, all of it combined makes up less than 5% of what actually exists in our universe. Let that sink in for a moment. Less than 5%. Everything humanity has ever observed, studied, or marveled at represents just a tiny fraction of reality. The rest, the overwhelming majority of our cosmos, remains hidden in plain sight. It's there, shaping the very structure of the universe, holding galaxies together, determining the fate of everything we know. Yet it's completely invisible to us. This invisible majority has a name, and it's one that might sound familiar, but whose true nature remains one of science's greatest puzzles. We call it dark matter. But that name is really just a placeholder, a confession of our ignorance wrapped in scientific terminology. Dark matter doesn't emit light. It doesn't absorb light. It doesn't reflect light. It doesn't interact with electromagnetic radiation in any way we can detect. It's called dark, not because it's some ominous cosmic force, but simply because we can't see it. Tonight, we're going to unravel this mystery together. We'll explore how scientists discovered something they couldn't see, why it's absolutely essential for the universe to work the way it does, and what it might actually be made of. We'll journey from the spinning edges of distant galaxies to the deepest theories of particle physics. We'll meet the brilliant minds who first glimpsed this cosmic shadow, and the modern researchers who are dedicating their lives to understanding it. But before we dive into the depths of this cosmic puzzle, let me tell you why this matters. Why should you care about something you can't see? Something that seems so far removed from your daily life? The answer is both humbling and profound. Dark matter isn't just some abstract concept floating around in the void of space. It's the invisible scaffolding that holds the entire universe together. Without it, galaxies wouldn't exist, stars wouldn't form, planets wouldn't coalesce. Life itself would never have had the chance to emerge. You see, dark matter is the cosmic architect that built the universe we inhabit. It's the hidden hand that guided the formation of every structure we see in the night sky. And understanding it might just be the key to unlocking the deepest secrets of reality itself. The story of dark matter begins not with grand theoretical predictions or complex mathematical equations, but with a simple observation that didn't make sense. Picture yourself as an astronomer in the 1930s, peering through telescopes at distant galaxies, trying to understand how these cosmic islands of stars hold themselves together. You know that gravity is what keeps everything bound, from planets orbiting stars to stars orbiting the centers of their galaxies. Common sense tells you that the stars on the outer edges of a galaxy should be moving slower than those near the center, just like planets in our solar system. Mercury races around the Sun much faster than distant Neptune. This is basic physics. The farther you are from the center of mass, the weaker gravity's pull becomes, and the slower you should orbit. But when astronomers actually measured the speeds of stars in distant galaxies, they discovered something that defied all expectations. The stars on the outer edges weren't moving slowly at all. In fact, they were whipping around the galactic center at speeds that should have sent them flying off into the cosmic void like sparks from a spinning wheel. According to everything we knew about gravity and motion, these galaxies should have torn themselves apart billions of years ago. This was the first glimpse of dark matter, though nobody called it that at the time. It was simply a profound mystery, a crack in our understanding of how the universe works. The galaxies were clearly holding together, but there wasn't nearly enough visible matter to provide the gravitational glue needed to keep them intact. Enter Vera Rubin, one of the most important astronomers you've probably never heard of. In the 1970s, Rubin and her colleague Kent Ford began a systematic study of galaxy rotation that would revolutionize our understanding of the cosmos. They focused on the Andromeda Galaxy, our nearest large galactic neighbor, and carefully measured the speeds of stars at various distances from its center. What they found was extraordinary and unsettling in equal measure. The rotation curve, as astronomers call it, was completely flat. Stars near the center moved at roughly the same speed as stars on the outer edges. This was like discovering that runners on the inside lane of a track were moving at the same speed as those on the outside lane, despite having a much shorter distance to cover. Rubin and Ford's observations were meticulous and undeniable. They had discovered that galaxies were embedded in vast halos of invisible matter, something that provided the extra gravitational pull needed to hold fast-moving outer stars in their orbits. This invisible matter had to be roughly 5 times more massive than all the visible stars, gas, and dust combined. The implications were staggering. If this was true for one galaxy, it was likely true for all galaxies. The universe was dominated by something we couldn't see, something that made up the majority of all matter in existence. It was a discovery that fundamentally changed our cosmic perspective, transforming us from inhabitants of a universe we thought we understood into explorers of a cosmos that was largely invisible and mysterious. But dark matter's influence extends far beyond individual galaxies. As astronomers began mapping the large-scale structure of the universe, they discovered that dark matter shapes the cosmic web itself. Imagine the universe as a vast, three-dimensional spider web, with galaxies strung along filaments of matter that stretch across billions of light years. These filaments intersect at massive nodes where galaxy clusters form, the largest gravitationally bound structures in the universe. This cosmic web exists because of dark matter. In the early universe, when everything was much smoother and more uniform, tiny variations in the density of dark matter acted as seeds. These slightly denser regions attracted more matter through their gravitational pull, growing larger and denser over time. Regular matter, the stuff that makes stars and planets, followed the gravitational lead of dark matter, falling into these growing wells of invisible mass. Over billions of years, this process sculpted the universe we see today. Dark matter provides the framework, the invisible skeleton upon which all visible structure hangs. Without it, the universe would be a smooth, featureless void, devoid of galaxies, stars, and life. The evidence for dark matter comes from multiple independent sources, each pointing to the same inescapable conclusion. Beyond galaxy rotation curves, we see its influence in the way light from distant objects gets bent and distorted as it passes through space. This effect, called gravitational lensing, occurs because massive objects curve the fabric of space and time itself, creating a kind of cosmic magnifying glass. When astronomers observe distant galaxies through massive galaxy clusters, they often see multiple distorted images of the same background galaxy, stretched and warped by the gravitational field of the cluster. By carefully analyzing these distortions, they can map the distribution of mass in the cluster. What they find is that most of the mass is invisible, distributed in ways that don't match the visible galaxies at all. Perhaps the most compelling evidence comes from colliding galaxy clusters, cosmic train wrecks that play out over millions of years. When two massive clusters collide, the hot gas between the galaxies interacts and slows down, creating drag and friction. But the dark matter, which barely interacts with anything, passes right through largely unaffected. This separation between visible matter and invisible matter provides a smoking gun for dark matter's existence. We can actually see the aftermath of these collisions, with the visible matter in one location and the gravitational effects of dark matter in another. It's like watching the shadows of invisible dancers, their presence revealed only by their gravitational choreography. The most famous example is the Bullet Cluster, two galaxy clusters that collided about 150 million years ago. The hot gas, glowing brightly in X-rays, was stripped away and left behind in the collision. But gravitational lensing reveals that most of the mass, the dark matter, continued onward with the galaxies themselves. This spatial separation between where we see the light and where we detect the gravitational effects provides some of the strongest evidence that dark matter is real and distinct from ordinary matter. As we continue our journey into this cosmic mystery, we'll explore what dark matter might actually be made of, the ingenious experiments scientists have devised to detect it, and why understanding this invisible majority might be the key to unlocking the deepest secrets of our universe. The story of dark matter is far from over. In fact, we're still in the early chapters of what may be the greatest detective story in the history of science. But for now, as you settle into this exploration, remember that you're surrounded by this mysterious substance right now. Dark matter particles are likely streaming through your body at this very moment, billions upon billions of them, completely unnoticed and unfelt. You're swimming in an invisible ocean of cosmic matter, part of a universe that is far stranger and more wonderful than our ancestors ever imagined. The question that haunts physicists around the world is elegantly simple, yet profoundly complex. What exactly is dark matter made of? It's a puzzle that has consumed some of the brightest minds of our generation, leading them down theoretical rabbit holes and into the deepest underground laboratories on Earth. The answer could reshape our understanding of reality itself. To appreciate the magnitude of this mystery, we need to understand what dark matter isn't. It's not made of atoms like you and me. It's not composed of protons, neutrons, and electrons dancing their familiar quantum ballet. Dark matter doesn't participate in the electromagnetic force that governs chemistry, light, and most of the phenomena we experience in our daily lives. It's something else entirely, something that exists in a parallel reality overlapping our own. Imagine two worlds occupying the same space. In one world, our familiar universe of stars and galaxies, light and chemistry, life and consciousness. In the other, a shadow universe of particles that feel only the pull of gravity, drifting through space like cosmic ghosts. These two worlds interact only through their gravitational embrace, each shaping the other's destiny while remaining largely invisible to one another. The leading candidates for dark matter particles read like a bestiary of theoretical physics, WIMPs, or weakly interacting massive particles, have long been the front runners in this cosmic race. These hypothetical particles would be heavy, perhaps dozens of times more massive than a proton, yet they would barely interact with ordinary matter. They could pass through your entire body, through the Earth itself, without disturbing so much as a single atom. Picture this for a moment. Right now, as you rest here listening to these words, trillions upon trillions of dark matter particles might be streaming through you at hundreds of kilometers per second. They flow through the walls of your room, through your bed, through your very cells, like cosmic rain that never gets you wet. You are completely transparent to them, and they to you, except for the faintest gravitational whisper that binds you both to the same cosmic dance. Scientists have built elaborate underground cathedrals dedicated to catching these elusive particles. Deep beneath mountains, shielded from cosmic rays and radioactive interference, sensitive detectors wait in perfect stillness for the rarest of events. A single dark matter particle, after eons of ghostly travel through space, might finally interact with a nucleus in their detector, creating a tiny flash of light or a microscopic vibration that could reveal the nature of the invisible universe. These experiments represent some of the most sensitive measurements ever attempted by human beings. They can detect energy deposits smaller than the metabolic activity of a single bacterium. They are cooled to temperatures colder than outer space and isolated from every possible source of contamination. Yet after decades of searching, they have found only tantalizing hints and puzzling anomalies, never the clear signal that would confirm dark matter's identity. But WIMPs are not the only suspects in this cosmic mystery. Axions, named after a laundry detergent because they were supposed to clean up problems in particle physics, represent another intriguing possibility. These particles would be incredibly light, millions of times lighter than an electron. Yet they could fill the universe in such vast numbers that their collective mass would account for all the dark matter we observe. Axions would be born from the quantum vacuum itself, emerging from the strange foam of virtual particles that underlies all of reality. They would be so weakly interacting that an axion could travel through a wall of lead several light years thick without being stopped. Yet in the presence of strong magnetic fields, these ghostly particles might occasionally transform into photons, creating a signal we could potentially detect. The search for axions has led to some of the most creative experiments in physics. Scientists have built resonant cavities cooled to near absolute zero, bathed in powerful magnetic fields, listening for the faint whisper of axions converting to microwaves. They've proposed using the magnetic field of the Sun itself as a giant axion telescope, watching for the subtle signature of these particles streaming from our star's core. Then there are the sterile neutrinos, hypothetical cousins of the ghostly neutrinos that already flood the universe. Unlike their known relatives, sterile neutrinos would interact only through gravity, making them perfect dark matter candidates. They would be produced in the early universe through quantum processes so subtle that even today we're not sure how they would work. Each of these possibilities opens different windows into the fundamental nature of reality. If dark matter is made of WIMPs, it suggests that our universe has an entire sector of particles and forces that we've never encountered. If axions are the answer, it points to deep connections between quantum mechanics and the structure of space and time itself. Sterile neutrinos would reveal new layers of complexity in the already mysterious world of neutrino physics. But perhaps the most radical possibility is that dark matter isn't a new type of particle at all. Maybe our understanding of gravity itself is incomplete. Modified theories of gravity, known by acronyms like MOND, suggest that the force of gravity behaves differently on cosmic scales than we expect. Perhaps there is no invisible matter, only invisible aspects of the gravitational force itself. These alternative theories face significant challenges in explaining all the observations that point to dark matter's existence. The way galaxies collide, the patterns we see in the cosmic microwave background, the formation of large-scale structure in the universe, all seem to require actual particles of dark matter rather than just modified gravity. Yet the possibility remains tantalizing, a reminder that our understanding of the cosmos may still have fundamental gaps. The search for dark matter has also led physicists to probe the very early universe, those first moments after the Big Bang, when the fundamental forces and particles that govern reality were still taking shape. In this primordial chaos, dark matter particles would have been created alongside the ordinary matter that makes up stars and planets. Computer simulations of cosmic evolution, fed with our best guesses about dark matter's properties, can recreate the large-scale structure of the universe with stunning accuracy. These simulations show how tiny quantum fluctuations in the early universe, amplified by dark matter's gravitational influence, eventually grew into the cosmic web of galaxies and voids we observe today. Yet for all our theoretical sophistication, dark matter continues to evade direct detection. Every few years, experiments report anomalous signals that could be dark matter, only to have them explained away by more mundane sources or fail to be confirmed by other detectors. The particles that make up most of our universe remain stubbornly elusive, hiding in plain sight throughout the cosmos. This elusiveness has led some scientists to wonder if we're approaching the problem from the wrong angle entirely. Maybe dark matter interacts with itself through forces we haven't considered. Maybe it has complex internal structure, forming its own dark atoms and dark chemistry. Maybe there's an entire dark sector of physics, with dark forces and dark interactions playing out invisibly alongside our familiar world. The implications of discovering dark matter's true nature extend far beyond academic curiosity. Understanding these particles could unlock new technologies we can barely imagine. If we could learn to manipulate dark matter, we might be able to probe the structure of space and time itself. We might discover new forms of energy or entirely new ways of interacting with the cosmos. As we continue our cosmic detective story, we'll explore the ingenious methods scientists have devised to track down these invisible particles. We'll journey to the deepest minds and the most remote laboratories, where researchers work tirelessly to solve one of the universe's greatest puzzles. The hunt for dark matter represents humanity at its most curious and determined, pushing the boundaries of knowledge into realms that challenge our very conception of reality. But the mystery deepens even further when we consider that dark matter is only part of a larger cosmic puzzle. The universe holds other secrets, other invisible components that shape its destiny in ways we're only beginning to understand. The story of the invisible universe is far richer and stranger than we ever imagined. The hunt for dark matter has taken scientists to some of the most extraordinary places on Earth. Deep beneath the Italian Alps, in a laboratory carved from solid rock a mile underground, physicists tend to their silent sentinels. These detectors, cooled to temperatures approaching absolute zero, wait in perfect stillness for an encounter that might happen only once in a human lifetime. Picture the dedication required for such work. Researchers spending decades of their careers on experiments that might never produce a single confirmed detection. They shield their instruments from cosmic rays, from radioactive decay, from the vibrations of trucks passing overhead. They create conditions cleaner than anything found in nature, more sterile than operating rooms, more isolated than the depths of space itself. In the Sanford Underground Research Facility in South Dakota, nearly a mile beneath the Black Hills, the LX Zeppelin experiment waits with liquid xenon so pure that a single atom of contamination could ruin years of careful measurement. The detector can sense energy deposits smaller than the warmth generated by a single bacterium. It represents one of humanity's most sensitive attempts to eavesdrop on the invisible universe. These underground cathedrals of science represent more than just experimental apparatus. They embody our deepest human impulse to understand, to peer beyond the veil of the obvious into realms that challenge everything we think we know about reality. The scientists who work in these facilities are modern-day explorers, venturing into territories more alien than any earthly frontier. But the search for dark matter extends far beyond terrestrial laboratories. High above the atmosphere, space-based detectors scan for the subtle signatures of dark matter particles colliding with cosmic rays. The Alpha Magnetic Spectrometer, mounted on the International Space Station, sifts through billions of cosmic particles, searching for the telltale excess of positrons that might signal dark matter annihilation in the galactic halo surrounding us. Each approach brings its own challenges and possibilities. Direct detection experiments underground hope to catch dark matter particles in the act of colliding with ordinary matter. Indirect detection searches look for the products of dark matter particles destroying each other in space. Collider experiments at facilities like CERN attempt to create dark matter particles in high-energy collisions, hoping to produce them in the laboratory under controlled conditions. The European Organization for Nuclear Research, known as CERN, houses the Large Hadron Collider, where protons smash together at energies approaching those present in the first moments after the Big Bang. In these collisions, scientists hope to create new particles that might reveal the nature of dark matter. They look for events where energy appears to vanish, carried away by invisible particles that escape their detectors without a trace. Yet for all this experimental ingenuity, dark matter continues to guard its secrets jealously. Each null result, each failed detection, teaches us something valuable about what dark matter is not, gradually narrowing the vast space of theoretical possibilities. But the absence of a clear signal also forces us to confront uncomfortable questions about our assumptions and methods. Perhaps dark matter interacts so weakly with ordinary matter that direct detection is fundamentally impossible with current technology. Perhaps it exists in forms so exotic that our theoretical frameworks are inadequate to describe them. Or perhaps the universe is trying to tell us something even more profound about the nature of reality itself. The theoretical landscape of dark matter has evolved dramatically as experimental constraints have tightened. Early models assumed dark matter particles would interact with ordinary matter through familiar forces just very weakly. But as detectors have grown more sensitive without finding these particles, theorists have been forced to consider increasingly exotic possibilities. Self-interacting dark matter presents one such possibility. Instead of being composed of particles that barely interact with anything, including each other, this dark matter would have its own rich internal dynamics. Dark matter particles might scatter off each other, forming bound states, even creating dark matter structures analogous to atoms and molecules. Imagine an entire shadow chemistry playing out invisibly around us. Dark atoms combining to form dark molecules, dark stars burning dark fuel, perhaps even dark planets harboring forms of organization and complexity we cannot imagine. This dark sector might be as rich and varied as our own visible universe, separated from us only by the barrier of electromagnetic interaction. The implications stretch the imagination. If dark matter has complex internal structure, it might form objects ranging from dark matter asteroids to dark matter black holes. These invisible structures would bend space and time, just like their ordinary matter counterparts, creating gravitational effects we might be able to detect, even if we cannot see the objects themselves. Some theories suggest that dark matter might not be composed of fundamental particles at all, but rather of composite objects formed in the early universe. Primordial black holes, created in the first moments after the Big Bang, when density fluctuations were extreme enough to trigger gravitational collapse, represent one such possibility. These primordial black holes could range in size from smaller than atoms to many times the mass of our Sun. Unlike the black holes formed from stellar collapse, primordial black holes could have any mass, limited only by the conditions present in the early universe. If they exist in sufficient numbers, they could account for all of dark matter without requiring any new fundamental particles. The search for primordial black holes has led astronomers to scan the skies for gravitational lensing events, brief brightenings of distant stars caused by invisible massive objects passing between us and them. These microlensing events last for days or weeks, creating temporary magnifications that reveal the presence of otherwise invisible matter. Yet another possibility emerges from the strange world of quantum field theory. Topological defects, created during phase transitions in the early universe, might persist as cosmic strings, domain walls, or monopoles. These exotic objects would be incredibly dense concentrations of energy, threading through space like invisible cosmic infrastructure. Cosmic strings, if they exist, would be thinner than atomic nuclei, but could stretch across the observable universe. They would create distinctive signatures in gravitational waves, patterns that might be detectable by current and future gravitational wave observatories. The discovery of such objects would revolutionize our understanding of both dark matter and the fundamental structure of space and time. The theoretical zoo of dark matter candidates continues to grow as physicists explore the mathematical landscapes opened by string theory extra dimensions, and supersymmetry. Each new theoretical framework suggests different possibilities for what dark matter might be, from Kaluza-Klein particles emerging from higher dimensions to the lightest supersymmetric partners of ordinary particles. Mirror matter presents perhaps the most poetic possibility. In this scenario, every particle in our universe has a mirror counterpart, identical in mass, but interacting only through gravity and possibly a mirror electromagnetic force. Mirror electrons would orbit mirror protons to form mirror atoms, which could combine into mirror molecules, mirror planets, even mirror life. This mirror universe would overlap our own spatially, but remain largely invisible to us. Mirror stars might shine with mirror light that we cannot see. Mirror planets might harbor mirror ecosystems. Mirror civilizations might contemplate their own version of the dark matter problem, wondering about the invisible ordinary matter that dominates their gravitational environment. The philosophical implications of such possibilities stretch our conception of reality itself. If dark matter represents an entire hidden sector of physics with its own particles, forces, and structures, then the universe is far stranger and more complex than we ever imagined. We might be living in just one layer of a cosmic onion, with entire worlds of physics playing out invisibly around us. As detection methods grow more sophisticated and theoretical understanding deepens, we edge closer to what may be one of the most profound discoveries in human history. The identification of dark matter's true nature will likely require not just better experiments or more clever theories, but perhaps entirely new ways of thinking about the relationship between the visible and invisible components of reality. The story continues to unfold in laboratories around the world, where dedicated researchers push the boundaries of what's possible in their quest to illuminate the cosmic dark. Each failed experiment brings valuable knowledge. Each theoretical breakthrough opens new avenues of investigation. The mystery of dark matter may be humanity's greatest scientific challenge, but it's also our greatest opportunity to discover just how magnificent and strange our universe truly is. Universe truly is. The search for dark matter has transformed from a curious astronomical observation into humanity's most ambitious scientific treasure hunt. Yet as we delve deeper into this cosmic mystery, we encounter something even more perplexing. The very methods we use to study the universe might be fundamentally limited when it comes to understanding dark matter's true nature. Consider the profound challenge facing researchers today. We're trying to study something that, by definition, doesn't interact with light or any other electromagnetic radiation. It's like trying to understand a symphony while being completely deaf, attempting to grasp the music only through the vibrations you can feel through the floor. Every tool in our astronomical arsenal, from the most powerful telescopes to the most sensitive spectrometers, relies on electromagnetic radiation. We're essentially trying to study the invisible using instruments designed to see. This limitation has forced scientists to become incredibly creative, developing entirely new ways of perceiving the universe. They've learned to read the gravitational signatures left by dark matter, like cosmic fingerprints, to interpret the bending of light around invisible masses, to decode the subtle patterns in cosmic background radiation that reveal dark matter's influence on the early universe. But perhaps the most fascinating aspect of dark matter research is how it's revealing the interconnected nature of cosmic phenomena. Dark matter doesn't exist in isolation. It's intimately connected to the formation of galaxies, the evolution of stars, the birth of planets, and ultimately, the emergence of life itself. Understanding dark matter means understanding the very foundations of cosmic architecture. In the early universe, when temperatures were so extreme that atoms couldn't form and matter existed only as a hot, dense plasma, dark matter was already hard at work. While ordinary matter was coupled to radiation and couldn't clump together effectively, dark matter felt only the pull of gravity. It began forming the first structures, creating the scaffolding upon which everything else would eventually build. Think of dark matter as the universe's urban planner, quietly designing the cosmic neighborhoods where galaxies would eventually take root. Without this invisible infrastructure, the universe would have remained smooth and featureless, a cosmic desert where no oases of complexity could form. Stars wouldn't have gathered into galaxies, planets wouldn't have coalesced from cosmic dust, and the intricate chemistry that makes life possible would never have had a chance to develop. This realization has profound implications for our understanding of our own existence. We are not separate from the dark matter mystery. We are intimately connected to it. The calcium in our bones, the iron in our blood, the carbon that forms the backbone of our DNA, all of these elements were forged in stars that formed within dark matter halos. We are quite literally children of the invisible universe, our very existence dependent on processes we're only beginning to understand. The scale of dark matter's influence becomes even more apparent when we examine the cosmic web, that vast network of filaments and voids that gives the universe its large-scale structure. Computer simulations reveal this web in stunning detail, showing how dark matter forms highways of gravity along which ordinary matter flows. Galaxy clusters form at the intersections of these highways, like cosmic cities at the crossroads of invisible interstate systems. These simulations represent some of the most complex calculations ever performed by human beings. They track the evolution of billions of particles over cosmic time, from the smooth early universe to the intricate web we observe today. The fact that these simulations can accurately reproduce what we see in the real universe, but only when dark matter is included, provides some of the strongest evidence for its existence. Yet the simulations also reveal puzzles within puzzles. They predict that dark matter should form dense, concentrated cores at the centers of galaxies. But observations suggest these cores are actually quite smooth. They predict vast numbers of small dark matter structures that should host tiny satellite galaxies. But we don't see nearly as many of these satellites as expected. These discrepancies have led to what astronomers call the small-scale crisis of dark matter theory. While dark matter explains the large-scale structure of the universe beautifully, its behavior on smaller scales remains mysterious. Perhaps dark matter particles interact with each other more than we thought, smoothing out the densest concentrations. Perhaps there are feedback mechanisms involving stars and black holes that we don't fully understand. Or perhaps our theoretical models are missing crucial physics. Some of the most intriguing possibilities involve dark matter's relationship with time itself. In the extreme environments near black holes, where space and time become severely warped, dark matter might behave in ways that challenge our understanding of both gravity and quantum mechanics. The event horizons of black holes might be places where dark matter accumulates in exotic states we can barely imagine. Recent discoveries in gravitational wave astronomy have opened entirely new windows into dark matter research. When black holes merge, they create ripples in space-time that carry information about the invisible matter surrounding them. These gravitational waves might reveal dark matter structures that are otherwise completely undetectable, providing our first direct glimpse of the invisible scaffolding that holds the universe together. The advanced LIGO detectors, sensitive enough to measure distortions in space smaller than 1/10,000th the width of a proton, are beginning to map the dark matter environment around merging black holes. Each detection adds another piece to the cosmic puzzle, revealing how dark matter behaves in the most extreme gravitational fields in the universe. But gravitational waves might tell us something even more profound about dark matter's nature. Some theoretical models predict that dark matter particles could be created or destroyed in the violent environments of black hole mergers, producing distinctive signatures in the gravitational wave signals. If confirmed, such discoveries would provide the first direct evidence of dark matter's particle nature. The hunt for these signatures requires incredible precision. Scientists must disentangle the complex waveforms produced by spinning, merging black holes from the subtle modifications that dark matter might create. It's like trying to hear a whispered conversation during a thunderstorm, requiring both exquisite sensitivity and sophisticated analysis techniques. Meanwhile, in laboratories around the world, the direct detection experiments continue their patient vigil. Each passing year without a clear signal forces researchers to push their instruments to ever greater levels of sensitivity. They've learned to distinguish between genuine dark matter interactions and the countless sources of background noise that plague underground detectors. The dedication required for these experiments is extraordinary. Researchers spend months preparing each run, carefully purifying their detector materials to remove every trace of radioactive contamination. They monitor their instruments continuously, watching for the subtle signs that might indicate a genuine dark matter interaction among the millions of background events. Some experiments have reported tantalizing hints of dark matter signals, only to see them disappear with improved analysis or additional data. The Dharma experiment in Italy has claimed to see an annual modulation in their detection rate, exactly what you'd expect, as Earth moves through the dark matter halo surrounding our galaxy. But other experiments using different detection methods have failed to confirm this signal. This pattern of tentative discoveries followed by null results has become a familiar frustration in dark matter research. Each claimed detection raises hopes that we're finally on the verge of a breakthrough, only to have those hopes dashed by more careful analysis or conflicting results from other experiments. Yet even these null results are valuable, gradually constraining the properties that dark matter particles can have. If dark matter were made of particles that interacted strongly with ordinary matter, we would have detected them by now. The fact that we haven't tells us something important about dark matter's elusive nature. The theoretical response to these experimental constraints has been to propose increasingly exotic forms of dark matter. Perhaps dark matter particles can only interact with ordinary matter through intermediate particles that are themselves very rare. Perhaps dark matter comes in multiple varieties, with only some types detectable by current experiments. Perhaps the interactions are so rare that we need detectors the size of mountains to have a reasonable chance of seeing them. Each of these possibilities pushes the boundaries of what we consider reasonable in particle physics. We're being forced to contemplate forms of matter so exotic that they challenge our fundamental assumptions about how particles should behave. Yet the gravitational evidence for dark matter's existence is so overwhelming that we have little choice but to take these exotic possibilities seriously. The philosophical implications of dark matter's elusiveness are profound. We're confronting the possibility that the universe contains entire categories of existence that are fundamentally beyond our direct experience. This invisible majority might operate according to physical laws we've never encountered, in ways that challenge our basic intuitions about reality. As we stand at this crossroads between the known and unknown, between the visible and invisible, we're reminded that the universe is under no obligation to be comprehensible to human minds. The fact that we can even perceive dark matter's gravitational influence, that we can deduce its existence through careful observation and reasoning, represents a remarkable achievement of human intellect and curiosity. The story of dark matter is far from over. New experiments are being planned, new theoretical frameworks are being developed, and new observational techniques are being pioneered. Space-based telescopes will soon map dark matter's distribution with unprecedented precision. Underground detectors will probe ever deeper into the realm of rare interactions. Particle accelerators will search for dark matter's signatures at higher and higher energies. Each of these efforts represents humanity's refusal to accept the limits of our current understanding. We are driven by an insatiable curiosity about the nature of existence itself, a desire to comprehend not just the 5% of the universe we can see, but the 95% that remains hidden in cosmic shadow. The invisible universe surrounding us continues to guard its secrets, but human ingenuity and persistence continue to chip away at the mystery. With each failed experiment, each refined theory, each new observation, we edge closer to understanding the true nature of the cosmic dark that shapes everything we know and are. But perhaps the most mind-bending aspect of dark matter research lies in what it reveals about the nature of observation itself. We're confronting a fundamental paradox that strikes at the heart of how we understand reality. Here we are, conscious beings made of ordinary matter, trying to comprehend a universe that is overwhelmingly composed of something we cannot directly perceive. It's as if we're inhabitants of a shadow world, catching only glimpses of the true cosmic architecture that surrounds us. This realization has led some physicists to propose radically different approaches to the dark matter problem. Instead of assuming that dark matter is simply another type of particle waiting to be discovered, they've begun to consider whether dark matter might represent something far more fundamental about the structure of space and time itself. Imagine that what we call dark matter isn't matter at all, but rather a manifestation of hidden dimensions curled up so tightly that we cannot perceive them directly. In these extra dimensions, familiar physics might operate according to different rules, creating gravitational effects that leak into our three-dimensional world like shadows cast by objects in a higher dimensional reality. String theory, that elegant mathematical framework, attempting to unify all the forces of nature, suggests that our universe might be a four-dimensional membrane floating in a higher dimensional space. Other membranes might exist parallel to ours, populated with their own particles and forces. The gravitational influence of matter on these parallel branes could be what we interpret as dark matter, making us unwitting observers of invisible parallel universes. This possibility transforms the dark matter mystery into something even more profound than the search for new particles. We might be glimpsing evidence of an entire multiverse of realities, each operating according to its own physical laws, yet all connected through the universal language of gravity. The dark matter halo surrounding our galaxy could be the gravitational signature of a parallel Milky Way, populated with forms of matter and energy we can barely imagine, but the implications go deeper still. If dark matter represents physics beyond our current understanding, then solving its mystery might require us to abandon some of our most cherished assumptions about the nature of reality. We might need to develop entirely new mathematical languages, new conceptual frameworks that can accommodate forms of existence that transcend our ordinary experience. The quantum nature of reality adds yet another layer of mystery to the dark matter puzzle. In the strange world of quantum mechanics, particles don't have definite properties until they're observed. They exist in superposition, occupying multiple states simultaneously until the act of measurement forces them to choose. What happens when this quantum weirdness is applied to dark matter on cosmic scales? Some theorists have proposed that dark matter might exist in quantum superposition across vast regions of space, creating gravitational effects that appear solid and definite to us, but are actually the result of quantum probability waves spanning entire galaxies. This would make dark matter not just invisible, but fundamentally uncertain, existing in a state of cosmic quantum indeterminacy that challenges our classical notions of what it means for something to be real. The measurement problem in quantum mechanics becomes even more perplexing when applied to dark matter. If dark matter particles are constantly in quantum superposition, what causes them to collapse into definite states? Perhaps the act of gravitational interaction itself serves as a kind of cosmic measurement, forcing dark matter to manifest its effects in the classical world we observe. This quantum perspective on dark matter opens up possibilities that stretch the imagination. Dark matter might exist in multiple parallel states simultaneously, creating gravitational effects that seem impossible from a classical perspective. The rotation curves of galaxies might be the result of quantum interference between different possible distributions of dark matter, creating patterns that appear random but are actually the result of deep quantum correlations. These ideas push us toward a view of the universe that is far stranger than anything our ancestors could have conceived. We're not just living in a cosmos dominated by invisible matter, but potentially in a reality where the very notion of existence is more fluid and uncertain than we ever imagined. The boundary between what exists and what doesn't might be far more blurred than our everyday experience suggests. The technological implications of understanding dark matter's true nature could be revolutionary. If dark matter is indeed a window into higher dimensions or parallel realities, learning to manipulate it might give us access to forms of energy and information that transcend our current understanding. We might discover ways to tap into the vast reservoir of dark energy that permeates space, or develop communication methods that operate through dimensions we cannot directly perceive. Imagine technologies that could interact directly with dark matter, allowing us to build structures that are partially anchored in invisible dimensions. Spacecraft that could navigate through dark matter, currents like sailing ships riding cosmic winds, communication systems that could transmit information through dark matter networks spanning galactic distances instantaneously. But perhaps the most profound implication of dark matter research is what it tells us about the nature of knowledge itself. We're discovering that the universe is under no obligation to reveal its secrets through the narrow channel of electromagnetic radiation. The cosmos operates on scales and through mechanisms that transcend our sensory experience, reminding us that reality is far larger and more complex than anything we can directly perceive. This humbling realization connects the dark matter mystery to the deepest questions of human existence. We are pattern-seeking creatures, evolved to make sense of the visible world around us. Yet we find ourselves in a universe where the most important patterns are invisible, where the dominant forces operate beyond our direct perception, where the very structure of reality might be fundamentally alien to our evolved intuitions. The search for dark matter has become a meditation on the limits and possibilities of human understanding. We're pushing the boundaries of what it means to know something, developing new ways of perceiving reality that go far beyond our biological senses. In doing so, we're not just solving a cosmic puzzle, but expanding the very definition of what it means to be conscious observers in an incomprehensibly vast and mysterious universe. Each underground detector, waiting in perfect silence, represents humanity's refusal to accept the boundaries of the visible world. Each theoretical breakthrough that pushes beyond the limits of ordinary experience demonstrates our willingness to follow the evidence wherever it leads, even into realms that challenge our most fundamental assumptions about the nature of existence. The story of dark matter is ultimately the story of human curiosity itself, our relentless drive to understand not just what we can see and touch, but the invisible forces that shape everything we are and everything we might become. In seeking to understand the cosmic dark, we're not just exploring the universe, but discovering new depths of our own capacity for wonder and comprehension. As we continue this journey into the invisible universe, we carry with us the recognition that we are part of something far grander and more mysterious than we ever imagined. The dark matter flowing through us at this very moment connects us to cosmic processes that span billions of years and countless light years of space. We are not separate from this mystery, but intimate participants in its unfolding. The particles streaming through your body as you rest here, the invisible scaffolding that holds the galaxies together, the quantum uncertainties that might govern the very nature of existence itself, all of these represent facets of a cosmic story that we're only beginning to read. Dark matter isn't just an astronomical curiosity. It's a reminder that we live in a universe of infinite depth and beauty, where the most profound truths often lie hidden in the spaces between the stars. Every breath you take occurs within a sea of invisible matter that has shaped the destiny of the cosmos since the first moments after the Big Bang. You are part of this invisible universe, connected to its mysteries through bonds that transcend ordinary understanding. In contemplating dark matter, we're not just studying distant galaxies and exotic particles, but exploring the very foundations of our own existence in a cosmos that continues to surprise and humble us with its magnificent complexity. The hunt continues in laboratories buried deep beneath the Earth, in observatories scanning the cosmic web, in the minds of theorists pushing the boundaries of human imagination. Each day brings new possibilities, new ways of thinking about the invisible majority that surrounds us. We stand at the threshold of discoveries that could transform our understanding of reality itself. guided by the gentle gravitational whispers of the cosmic dark that has been patiently waiting for us to learn how to listen. The implications of our dark matter discoveries ripple outward in ways that transform not just astronomy, but our entire relationship with the concept of reality itself. As we stand here tonight, surrounded by this invisible ocean of cosmic matter, we're confronting questions that our species has never had to ask before. What does it mean to live in a universe where most of existence remains hidden from our direct experience? Picture yourself as a detective trying to solve a mystery where you can never see the crime scene directly. You can only study the shadows cast on the wall, the footprints left in mud, the way objects move when touched by invisible hands. This is precisely the situation we find ourselves in with dark matter. We're cosmic detectives, piecing together clues from gravitational effects, from the way light bends around invisible masses, from the patterns etched into the cosmic microwave background radiation. The detective work has led us to some startling realizations about the architecture of our universe. Dark matter doesn't just exist in distant galaxies. It forms an intricate web that connects everything in the cosmos, a vast network of invisible filaments stretching across billions of light years. These dark matter highways determine where galaxies form, where stars are born, where planets coalesce from cosmic dust. Think of it as the universe's circulatory system, invisible arteries carrying the gravitational influence that nourishes cosmic structure. Just as blood vessels in your body create pathways for nutrients to flow, these dark matter filaments create pathways along which ordinary matter travels through space. The galaxy containing your home, the star that warms your world, the very atoms that make up your body, all followed these invisible roads on their journey through cosmic time. But here's where the story becomes even more extraordinary. Recent computer simulations have revealed that this dark matter web isn't random or chaotic. It displays patterns, symmetries, and organizational principles that suggest deep underlying order in the universe. The invisible scaffolding that holds everything together follows mathematical rules so elegant and precise that they seem almost artistic in their beauty. These simulations can reproduce the observed universe with stunning accuracy, but only when dark matter is included in the calculations. Remove dark matter from the equations, and the simulated universe becomes a smooth, featureless void where no complex structures can form. Add dark matter back in, and suddenly galaxies bloom like flowers along invisible stems. Clusters form at the intersections of cosmic highways, and the rich tapestry of cosmic structure unfolds exactly as we observe it in the real universe. This predictive power represents one of science's greatest triumphs, yet it also highlights the profound mystery we're dealing with. We can model dark matter's behavior with mathematical precision. We can predict its effects on cosmic evolution. We can trace its influence from the earliest moments after the Big Bang to the present day. But we still don't know what it actually is. The search has led scientists to contemplate possibilities that stretch the boundaries of imagination. Perhaps dark matter particles are their own antiparticles, capable of annihilating themselves in flashes of pure energy when they collide. Perhaps they decay over cosmic timescales, slowly transforming into other exotic particles we've never encountered. Perhaps they form complex bound states, dark matter versions of atoms and molecules, creating an entire periodic table of invisible elements. Some of the most intriguing theories suggest that dark matter might not be composed of particles at all, but rather of topological defects in the fabric of space-time itself. Imagine the universe as a cosmic crystal, and dark matter as the invisible flaws and dislocations that give this crystal its strength and structure. These defects would bend space and time around them, creating gravitational effects without requiring any actual matter. Other theories venture even further into the realm of the exotic. Perhaps dark matter exists in extra dimensions that we cannot perceive, leaking gravitational influence into our three-dimensional world, like shadows cast by objects in a higher dimensional reality. Perhaps it represents the boundary between our universe and parallel realities, a cosmic membrane that separates different domains of existence while allowing gravity to pass between them. The philosophical implications of these possibilities are staggering. We might be living in just one layer of a multidimensional cosmic onion, with entire universes of dark matter existing parallel to our own. These parallel realities might operate according to different physical laws, harbor different forms of complexity, perhaps even different forms of consciousness that we could never directly encounter. This brings us to one of the most haunting questions in all of dark matter research. If there's an entire invisible sector of physics operating around us, could there be invisible forms of life as well? Could dark matter organize itself into complex structures capable of information processing, pattern recognition, even some form of awareness? The possibility seems remote, but not impossible. After all, consciousness emerged from ordinary matter through processes we still don't fully understand. If dark matter has its own rich internal dynamics, its own forces and interactions, there's no fundamental reason why it couldn't give rise to forms of organization and complexity that we would recognize as life. Imagine dark matter creatures swimming through space like cosmic jellyfish, following magnetic field lines and feeding on the energy of stellar winds. Picture dark matter ecosystems existing within the halos of galaxies, invisible biospheres where evolution has been operating for billions of years. Consider the possibility that dark matter civilizations might already exist, contemplating their own version of the ordinary matter problem, wondering about the strange visible stuff that makes up such a small fraction of their universe. These speculations venture far beyond current scientific evidence, but they illustrate the profound implications of living in a universe dominated by invisible matter. We're not just dealing with a missing component in our cosmic inventory, but potentially with entire categories of existence that operate beyond our ability to perceive directly. The technological challenges of studying dark matter have pushed human ingenuity to extraordinary limits. Deep underground, in caverns carved from ancient rock, scientists have created the most sensitive detectors ever built. These instruments can register energy deposits smaller than the warmth generated by a single radioactive decay, vibrations fainter than the footstep of an ant walking across the detector surface. The level of precision required is almost beyond comprehension. Imagine trying to detect the impact of a single snowflake while standing next to a thundering waterfall. That's essentially what dark matter researchers are attempting, searching for the incredibly rare interactions of dark matter particles against a background of countless other subatomic processes. These detectors must be shielded from cosmic rays, isolated from radioactive contamination, protected from vibrations, and cooled to temperatures approaching absolute zero. The materials used in their construction must be purified to levels that exceed anything found in nature. A single atom of the wrong isotope could create a false signal that might be mistaken for dark matter. The dedication required for such work represents human curiosity at its most refined and persistent. Researchers spend entire careers building and operating instruments that might never produce a clear detection. They monitor their equipment 24 hours a day, analyzing every signal, every fluctuation, every anomaly that might hint at dark matter's presence. Yet even in the absence of direct detection, these experiments are teaching us valuable lessons about the nature of reality. Each null result constrains the properties that dark matter particles can have. Each failed detection eliminates another theoretical possibility, gradually narrowing the vast space of what dark matter might be. This process of elimination has led to increasingly exotic theoretical proposals. If dark matter particles interacted strongly with ordinary matter, we would have detected them by now. The fact that they remain hidden tells us that any interactions must be extraordinarily weak, perhaps mediated by forces we've never encountered or occurring through mechanisms that barely affect ordinary matter. Some theories propose that dark matter particles can only interact with ordinary matter through intermediate particles that are themselves incredibly rare. Others suggest that the interactions might depend on specific conditions of temperature, pressure, or magnetic field strength that are difficult to reproduce in laboratory settings. Still others propose that dark matter might be composed of multiple particle types, with only certain varieties detectable by current methods. Each of these possibilities pushes the boundaries of particle physics into uncharted territory. We're being forced to contemplate forms of matter so exotic that they challenge our basic understanding of how particles should behave. Yet the gravitational evidence for dark matter's existence is so overwhelming that we must take these exotic possibilities seriously. The international collaboration required for dark matter research has created a global community of scientists united by their shared fascination with the invisible universe. Teams from different countries share data, compare results, and work together to solve technical challenges that no single nation could tackle alone. This cooperation represents humanity at its best, transcending political boundaries in pursuit of cosmic understanding. The experiments themselves have become marvels of international engineering. The Large Hadron Collider at CERN involves thousands of scientists from dozens of countries, all working together to recreate the conditions present in the first moments after the Big Bang. Underground detectors in Italy, South Dakota, and Canada coordinate their searches, comparing signals and cross-checking results to ensure that any claimed discovery can be independently verified. This global effort reflects the magnitude of what we're attempting to understand. Dark matter isn't just a local phenomenon affecting our galaxy or our cosmic neighborhood. It's a universal feature of reality, present everywhere in the cosmos, shaping the evolution of every galaxy, every star system, every planet that has ever formed. As you rest here tonight, dark matter particles are streaming through you at incredible speeds, billions upon billions of them passing through your body every second. They've been traveling through space for eons, carrying with them the gravitational history of cosmic evolution. Some might have originated in the dark matter halo surrounding our galaxy. Others might have journeyed from distant galaxy clusters, carrying information about cosmic structures billions of light years away. You are quite literally swimming in an ocean of invisible matter that connects you to the deepest processes of cosmic evolution. The same dark matter that shapes the large-scale structure of the universe flows through the space between your atoms, linking you intimately to the cosmic web that spans the observable universe. This connection isn't just poetic metaphor. The dark matter in your immediate vicinity influences the motion of our solar system through the galaxy. It affects the gravitational environment that has guided the evolution of life on Earth. The invisible particles passing through you right now are part of the same cosmic infrastructure that made your existence possible. The realization that we're embedded within dark matter's invisible embrace has profound implications for how we understand our place in the cosmos. We're not separate observers studying the universe from the outside. We're integral participants in cosmic processes that operate on scales far beyond our everyday experience. Every breath you take occurs within a gravitational field shaped by dark matter. Every heartbeat happens in space that's filled with invisible particles carrying the momentum of cosmic evolution. You are not just made of star stuff, as Carl Sagan famously observed. You are also intimately connected to the dark matter infrastructure that made those stars possible in the first place. This perspective transforms dark matter from an abstract scientific problem into something deeply personal. Understanding dark matter means understanding the invisible foundations of our own existence. It means comprehending the cosmic processes that created the conditions necessary for complexity, consciousness, and life itself to emerge from the primordial simplicity of the early universe. As we continue our journey into this cosmic mystery, we carry with us the recognition that we're not just studying distant phenomena, but exploring the very nature of the reality we inhabit. The dark matter mystery is ultimately about understanding our own cosmic heritage, the invisible threads that connect us to the birth and evolution of everything we know and are. The story continues to unfold in laboratories and observatories around the world, where dedicated researchers push the boundaries of human knowledge in their quest to illuminate the cosmic dark. Each experiment brings new possibilities. Each theoretical breakthrough opens new avenues of understanding. Each observation adds another piece to the magnificent puzzle of existence. We stand at the threshold of discoveries that could transform our understanding of reality itself, guided by the invisible presence that has been shaping cosmic destiny since the first moments after the Big Bang. The dark matter flowing around us and through us connects us to mysteries that span the entire history of the universe, reminding us that we are part of something far grander and more complex than we ever imagined. In contemplating dark matter, we're not just studying the invisible majority of the cosmos. We're exploring the hidden foundations of existence itself, discovering new depths of mystery and beauty in a universe that continues to surprise us with its magnificent complexity. The cosmic dark that surrounds us holds secrets that may reshape our understanding of what it means to exist in this strange and wonderful reality we call home. The quest to understand dark matter has taken us to places where science meets philosophy, where hard data collides with profound questions about the nature of existence itself. As we venture deeper into this cosmic mystery, we encounter something that challenges not just our theories, but our entire framework for understanding what it means to know something about the universe. Consider the extraordinary position we find ourselves in as conscious observers, trying to comprehend the invisible majority of reality. We've developed instruments of incredible sensitivity, theories of breathtaking mathematical elegance, and experimental techniques that push the boundaries of what's physically possible. Yet dark matter continues to elude our grasp, remaining tantalizingly beyond the reach of direct confirmation. This elusiveness has led some researchers to question whether we're approaching the problem from the right direction entirely. Perhaps the issue isn't that our detectors aren't sensitive enough, or our theories aren't sophisticated enough. Perhaps the challenge is more fundamental, rooted in the very nature of how consciousness interacts with reality. Think about it for a moment. We are beings made of ordinary matter, creatures whose entire evolutionary history has been shaped by electromagnetic interactions. Our eyes detect photons, our brains process electrical signals, our bodies are held together by chemical bonds. Everything about our existence is intimately tied to the electromagnetic force. Yet we're trying to study something that, by definition, doesn't participate in electromagnetic interactions at all. It's as if we're fish trying to understand the air above the water's surface. We can see its effects, the way it bends light at the interface, the way objects move differently when they breach the surface. But the medium itself remains foreign to our direct experience. We lack the sensory apparatus, the evolutionary background, even the conceptual framework to truly comprehend what exists beyond our electromagnetic realm. This realization has profound implications for the future of dark matter research. Perhaps direct detection, the holy grail that has driven so much experimental effort, represents a fundamental category error. Perhaps we're like ancient philosophers trying to understand the nature of fire by analyzing the shadows it casts on cave walls. We can learn about its effects, its influence, its role in cosmic evolution, but the essence itself might remain forever beyond our reach. But here's where the story takes a remarkable turn. Even if dark matter remains directly undetectable, its gravitational signature tells a story of cosmic evolution that's both beautiful and deeply meaningful. Through careful observation and ingenious analysis, we've learned to read the invisible handwriting that dark matter has left across the cosmos. Galaxy rotation curves become cosmic calligraphy, each one telling us about the invisible mass distribution that holds stellar systems together. Gravitational lensing transforms distant galaxies into cosmic manuscripts, their distorted shapes encoding information about the dark matter structures between us and them. The cosmic microwave background becomes a fossil record of dark matter's influence on the early universe, its subtle temperature variations preserving the memory of invisible density fluctuations from nearly 14 billion years ago. These observations have allowed us to construct what might be the most successful model in the history of science. The lambda-CDM model, incorporating both dark matter and dark energy, can account for observations spanning the entire observable universe, from the smallest galaxy satellites to the largest cosmic structures. It describes how the universe evolved from the smooth, simple state revealed by the cosmic microwave background to the rich, complex tapestry of galaxies and clusters we observe today. Yet this very success raises troubling questions about the nature of scientific knowledge itself. We have a model that works extraordinarily well, that makes precise predictions about cosmic evolution, that has passed every observational test we can devise. But it requires us to accept that most of the universe consists of components we don't understand and may never be able to study directly. This situation is unprecedented in the history of science. Previous mysteries, no matter how challenging, always held out the promise of eventual direct investigation. We might not have been able to see atoms initially, but we could eventually develop instruments sensitive enough to detect them. We might not have understood the nature of stars, but we could analyze their light and deduce their composition and evolution. Dark matter presents us with something different, a phenomenon that might be fundamentally beyond the reach of direct study, yet whose existence is so well established that denying it would require abandoning our most successful theories of cosmic evolution. We're being forced to accept a new category of scientific knowledge, one based on inference and indirect detection, rather than direct observation and manipulation. This shift has philosophical implications that extend far beyond astronomy and physics. We're discovering that the universe contains aspects of reality that transcend our ability to experience them directly, yet which are absolutely crucial for understanding how everything works. It's a humbling reminder that consciousness, for all its remarkable capabilities, represents just one narrow window into the nature of existence. The search for dark matter has also revealed something profound about the relationship between observation and reality. In quantum mechanics, we've grown accustomed to the idea that the act of observation can affect what we observe. But dark matter presents us with the opposite situation. Here's a phenomenon that affects everything we can observe, yet which itself remains unobservable by conventional means. This has led some theorists to propose that dark matter might exist in a fundamentally different relationship to space and time than ordinary matter. Perhaps it inhabits dimensions we cannot perceive, creating gravitational effects that leak into our three-dimensional world, like shadows cast by objects in higher dimensional space. Perhaps it exists in a state of perpetual quantum superposition, manifesting its effects through probability waves that span galactic distances. These possibilities push us toward a view of reality that's far stranger than anything our everyday experience suggests. We might be living in just one layer of a multidimensional cosmos, with entire universes of dark phenomena playing out invisibly around us. The gravitational effects we attribute to dark matter might be glimpses of physics operating in realms that transcend our normal conception of space and time. But even as we contemplate these exotic possibilities, the practical search for dark matter continues with renewed intensity and creativity. New generations of detectors, each more sensitive than the last, continue their patient vigil in underground laboratories around the world. Space-based observatories map the distribution of dark matter through gravitational lensing with unprecedented precision. Particle accelerators probe higher and higher energies, searching for any sign of dark matter production in their collision chambers. Each approach brings its own unique perspective to the puzzle. Direct detection experiments hope to catch dark matter particles in the act of interacting with ordinary matter, providing the definitive proof that these invisible particles actually exist. Indirect detection searches look for the products of dark matter annihilation or decay, scanning the sky for gamma rays, neutrinos, or other particles that might be produced when dark matter particles destroy each other. Collider experiments take a different approach entirely, attempting to create dark matter particles in high-energy collisions, and then inferring their presence from missing energy and momentum in the collision debris. These experiments operate at energies approaching those present in the first moments after the Big Bang, recreating conditions that haven't existed in the universe for nearly 14 billion years. The international collaboration required for these efforts has created a global community of researchers united by their shared fascination with the invisible universe. Teams from different countries, different cultures, different scientific traditions work together, sharing data and insights in pursuit of understanding that transcends any national or institutional boundary. This cooperation represents something beautiful about human nature. Faced with a mystery that challenges our most basic assumptions about reality, we respond not with resignation or despair, but with increased determination and creativity. We build more sensitive instruments, develop more sophisticated theories, devise more ingenious experiments. We refuse to accept the limitations of our current understanding. The dark matter mystery has also sparked remarkable innovations in technology and methodology. The ultra-pure materials required for underground detectors have led to advances in purification techniques that benefit multiple industries. The sophisticated data analysis methods developed to search for rare dark matter interactions have applications in medical imaging, environmental monitoring, and financial modeling. The computational challenges of simulating cosmic evolution have driven advances in high-performance computing that benefit climate science, drug discovery, and artificial intelligence research. The precision required for gravitational wave detection has led to innovations in laser interferometry that enhance our ability to measure tiny distances and detect subtle vibrations. These technological spillovers remind us that fundamental research, even when focused on seemingly abstract questions, often produces practical benefits that were impossible to anticipate. The quest to understand dark matter is not just about satisfying scientific curiosity, but about pushing the boundaries of human capability in ways that ultimately benefit all of society. As we stand at this crossroads between the known and unknown, between the visible and invisible, we're reminded that science is ultimately about more than just accumulating facts or developing technologies. It's about expanding our conception of what's possible, challenging our assumptions about the nature of reality, and pushing against the boundaries of human understanding. The dark matter mystery embodies all of these aspects of scientific inquiry. It forces us to confront the limits of our observational capabilities, while simultaneously inspiring us to transcend those limits through creativity and persistence. It challenges our theoretical frameworks while opening new avenues of investigation that we never could have imagined. Most importantly, it reminds us that we are part of something far grander and more mysterious than our everyday experience suggests. The invisible matter flowing through us at this very moment connects us to cosmic processes that span billions of years and countless light years of space. We are not separate from the dark matter mystery, but intimate participants in its unfolding. Every breath you take occurs within a gravitational field shaped by invisible matter. Every heartbeat happens in space permeated by particles that have traveled across the cosmos. You are embedded within the very phenomenon we're trying to understand, part of the cosmic web that dark matter has spent billions of years constructing. This perspective transforms dark matter research from an abstract intellectual exercise into something deeply personal and profound. We're not just studying distant galaxies and exotic particles, but exploring the hidden foundations of our own existence. Understanding dark matter means understanding the invisible architecture that made our universe, our galaxy, our solar system, and ultimately our own lives possible. The story continues to unfold in laboratories and observatories around the world, where dedicated researchers push forward in their quest to illuminate the cosmic dark. Each null result teaches us something valuable about what dark matter is not, gradually constraining the theoretical possibilities. Each new observation adds another piece to the magnificent puzzle of cosmic evolution. We may never solve the dark matter mystery completely. We may never develop instruments sensitive enough to detect these elusive particles directly. We may never fully understand the nature of the invisible majority that surrounds us. But in the attempt itself, in the persistent effort to comprehend what lies beyond our direct experience, we discover something essential about what it means to be conscious beings in an incomprehensibly vast and mysterious universe. The dark matter flowing around you right now carries with it the entire history of cosmic evolution, from the first moments after the Big Bang to the formation of the cosmic web that shapes our universe today. In contemplating its mystery, you're connecting with the deepest questions about the nature of existence itself, joining a quest for understanding that may represent the highest expression of human curiosity and wonder. As you rest here tonight, surrounded by this invisible ocean of cosmic matter, remember that you are part of the story we're trying to tell. The dark matter mystery isn't something happening out there in distant space, but something intimately connected to your own existence in a universe that continues to surprise us with its magnificent complexity and beauty. The search for dark matter has become humanity's most patient and persistent scientific endeavor, a cosmic game of hide and seek that has stretched across decades of careful observation and ingenious experimentation. Yet as we stand on the threshold of potentially revolutionary discoveries, we find ourselves confronting possibilities that are both more exotic and more profound than anything we initially imagined. Deep beneath the mountains of Italy, in chambers carved from solid rock and shielded from every possible source of interference, the Xenon collaboration tends to their crystalline detectors with the dedication of monks guarding sacred relics. These instruments, filled with liquid xenon so pure that it makes distilled water look contaminated, represent the pinnacle of human precision in the art of cosmic detection. Picture the extraordinary sensitivity required for their work. These detectors must distinguish between the genuine whisper of a dark matter particle and the countless false signals that bombard them every second. Cosmic rays, radioactive decay from the surrounding rock, even the minute vibrations from trucks passing overhead, miles above, all create background noise that could mask the signal they're desperately seeking. The researchers have learned to read the signatures of individual atomic interactions with the skill of forensic investigators examining crime scenes. Each flash of light, each tiny electrical pulse, each subtle pattern in their data could potentially be the long-awaited evidence of dark matter's direct touch upon ordinary matter. They've spent years learning to distinguish the authentic from the spurious, developing techniques so refined that they can identify the source of contamination from a single radioactive atom hiding among trillions of xenon nuclei. But the underground laboratories represent just one front in this multifaceted campaign to unmask the invisible universe. High above the Earth's atmosphere, the alpha magnetic spectrometer aboard the International Space Station sweeps through cosmic rays with the persistence of a cosmic archaeologist. sifting through millions of particles in search of the subtle excess that might signal dark matter's destruction in the depths of space. This space-based detective work requires a different kind of patience and precision. Unlike the underground experiments that wait for dark matter to come to them, the AMS actively samples the cosmic particle shower that bathes our solar system, analyzing each cosmic ray for clues about its origins and composition. The researchers must account for every possible source of the particles they detect, from distant supernova explosions to the acceleration mechanisms around black holes. The data they collect tells stories of cosmic violence played out across galactic distances. High-energy protons carry the signatures of stellar explosions that occurred millions of years ago. Heavier nuclei bear the marks of their acceleration in the magnetic fields surrounding neutron stars. But hidden among these familiar cosmic messengers might be particles born from the annihilation of dark matter, carrying with them the first direct evidence of what this invisible substance actually is. Meanwhile, in the tunnels beneath the Swiss-French border, the Large Hadron Collider pushes protons to energies that existed only in the first moments after the Big Bang. Here, researchers attempt the ultimate act of cosmic archaeology, recreating the conditions present when dark matter was first forged in the primordial fire of creation itself. The approach is audaciously direct. If dark matter particles were created in the early universe, then perhaps we can create them again by colliding ordinary particles at sufficient energies. The challenge lies in detecting particles that, by definition, barely interact with the sophisticated detectors surrounding the collision point. The physicists have learned to search for the invisible through its absence. When two protons collide at nearly the speed of light, the explosion of energy creates a shower of particles that spray outward in all directions. Every particle is tracked, every trajectory measured, every energy deposit recorded with exquisite precision. But sometimes, when they add up all the energy and momentum they can detect, the books don't balance. Something is missing. Something has carried away energy and momentum while leaving no trace in their detectors. These missing energy events could be the signature of dark matter particles created in the collision and then escaping undetected into the cosmos. It's like watching a magic trick in reverse, where the disappearance of something reveals its presence rather than concealing it. Each collision represents a brief recreation of cosmic conditions that haven't existed for nearly 14 billion years, a momentary window into the fundamental processes that shaped our universe. But the search for dark matter extends far beyond these terrestrial laboratories. Astronomers have learned to use the entire cosmos as their experimental apparatus, turning telescopes toward distant galaxy clusters where dark matter's gravitational influence creates natural experiments of unprecedented scale. When massive galaxy clusters collide, they create cosmic laboratories where the properties of dark matter are revealed through their gravitational choreography. These collisions, which unfold over millions of years, allow us to watch dark matter in action as it separates from ordinary matter during the cosmic crash. The Bullet Cluster, that famous cosmic collision we've glimpsed before, continues to yield insights into dark matter's nature. But it's no longer unique. Astronomers have discovered dozens of similar systems, each one providing additional clues about how dark matter behaves under extreme conditions. Some collisions show clean separations between visible and dark matter, confirming that dark matter barely interacts with itself. Others reveal more complex dynamics that hint at subtle interactions we're only beginning to understand. The precision required to extract meaningful information from these cosmic experiments is extraordinary. Astronomers must map the distribution of mass through gravitational lensing, tracking how the gravity of invisible dark matter bends and distorts the light from background galaxies. They must measure the temperatures and densities of the hot gas that fills the space between galaxies. Understanding how this gas responds to the gravitational forces during cosmic collisions. Each observation requires months of careful analysis, separating genuine gravitational effects from instrumental artifacts and atmospheric distortions. The researchers have become experts at reading the subtle signatures that dark matter leaves in the patterns of distorted galaxies, learning to decode messages written in the language of curved spacetime itself. But perhaps the most remarkable aspect of modern dark matter research is how it has transformed our understanding of the relationship between theory and observation. Traditional physics often proceeds from theoretical predictions to experimental verification. Scientists develop mathematical models, make predictions, and then design experiments to test those predictions. Dark matter research has largely proceeded in the opposite direction. The phenomenon was discovered through observations that contradicted theoretical expectations. The existence of dark matter was forced upon us by data that refused to conform to our understanding of how the universe should work. Only after accepting its existence did theorists begin the challenging task of explaining what it might be. This reversal has created a unique dynamic in the field. Experimentalists continue to push the boundaries of detection sensitivity, while theorists work to keep pace with increasingly exotic possibilities. Each null result from underground detectors forces theorists to consider more weakly interacting particles. Each new astronomical observation adds constraints that eliminate entire classes of theoretical models. The interplay between observation and theory has led to an explosion of creative possibilities. Dark matter might be composed of particles that interact only through gravity and the weak nuclear force. It might consist of particles so light they behave more like waves than discrete objects, forming cosmic structures through quantum interference effects. It might include multiple particle types, creating an entire dark sector of physics with its own forces and interactions. Some of the most intriguing recent proposals suggest that dark matter might undergo phase transitions, changing its properties as the universe cools and expands. Early in cosmic history, dark matter might have interacted more strongly, allowing it to form complex structures before decoupling into the nearly invisible state we observe today. This could explain why computer simulations sometimes predict dark matter distributions that don't quite match observations. Other theories propose that dark matter might be unstable, slowly decaying into other particles over cosmic timescales. This decay would be unimaginably slow by human standards, with individual particles surviving for billions of times the current age of the universe before finally transforming. But over cosmic time, this decay might produce detectable signatures in the form of high-energy photons or exotic particles streaming from regions of high dark matter density. The possibility of dark matter decay opens up entirely new avenues for detection. Instead of waiting for dark matter particles to interact with terrestrial detectors, astronomers could search for the products of dark matter decay in the cosmic radiation background. These searches require incredible precision. looking for tiny excesses in gamma-ray emissions from the centers of galaxies, or subtle distortions in the spectra of cosmic microwave background radiation. Each of these theoretical possibilities requires different experimental approaches, different analysis techniques, different ways of interpreting the data we collect. The field has become a complex ecosystem of interconnected searches, each one probing different aspects of dark matter's potential nature. Underground direct detection experiments continue to push toward ever greater sensitivity, but they've also diversified their approaches. Some experiments use liquid xenon targets, others employ crystalline detectors cooled to near absolute zero. Some search for nuclear recoils caused by dark matter collisions. Others look for the excitation of electrons or the breaking of chemical bonds. Space-based indirect detection searches have similarly proliferated. Different experiments focus on different energy ranges, different regions of the sky, different types of cosmic radiation. Some look for gamma rays from dark matter annihilation. Others search for cosmic ray positrons or antiprotons that might be produced when dark matter particles destroy each other. The diversity of approaches reflects both the uncertainty about dark matter's true nature and the determination of the scientific community to leave no stone unturned in the search for understanding. Researchers have learned that dark matter might reveal itself through any number of different signatures, and they've designed their experiments accordingly. But perhaps the most profound development in dark matter research has been the growing recognition that we might need to fundamentally revise our expectations about what constitutes a successful detection. The classical model of scientific discovery, where a clear experimental signal provides unambiguous evidence for a theoretical prediction, might not apply to something as elusive as dark matter. Instead, we might need to piece together the puzzle from multiple independent lines of evidence, none of which alone provides definitive proof, but which collectively paint a compelling picture of dark matter's existence and properties. This approach requires a new kind of scientific patience, a willingness to build understanding gradually through the accumulation of subtle clues rather than dramatic revelations. The cosmic microwave background has already provided one example of this approach. The tiny temperature fluctuations in this ancient radiation carry the imprint of dark matter's influence on the early universe. But extracting this information requires incredibly sophisticated analysis of incredibly subtle signals. No single measurement provides obvious evidence for dark matter, but the overall pattern of fluctuations can only be explained by invoking invisible matter in precisely the amounts predicted by dark matter theory. Future observations promise to extend this approach to new realms of precision and subtlety. The Euclid Space Telescope will map the shapes and positions of billions of galaxies with unprecedented accuracy, allowing astronomers to trace dark matter's influence across cosmic history through gravitational lensing effects. The Vera Rubin Observatory will monitor the sky continuously for years, watching for the subtle changes that might reveal dark matter's presence through its gravitational effects on the orbits of asteroids and comets. These surveys will generate datasets of almost incomprehensible size and complexity. Processing and analyzing the data will require advances in artificial intelligence and machine learning that push the boundaries of computational science. The search for dark matter is driving innovation not just in detector technology and theoretical physics, but in the fundamental methods we use to extract meaning from vast amounts of observational data. The challenges are immense, but so is the potential reward. Understanding dark matter means understanding the invisible scaffolding that holds the universe together, the hidden architecture that made galaxies, stars, planets, and ultimately life itself possible. It means comprehending forces and particles that operate according to physical laws we've never encountered, in realms of existence that transcend our everyday experience. As you settle deeper into contemplation of these cosmic mysteries, remember that the dark matter particles streaming through you at this very moment carry with them the entire history of the universe. They've witnessed the birth of the first stars, the formation of the first galaxies, the slow construction of the cosmic web that shapes everything we see in the night sky. You are not separate from this invisible universe, but intimately connected to it through bonds that operate at the deepest levels of physical reality. The same gravitational forces that guide dark matter through cosmic space also influence the motion of your body through the galaxy, connecting you to processes that span billions of years and countless light years of space. The quest to understand dark matter continues in laboratories and observatories around the world, where dedicated researchers work tirelessly to solve one of the greatest puzzles in the history of science. Each day brings new data, new theoretical insights, new experimental techniques that edge us closer to comprehending the invisible majority that surrounds us. We stand at the threshold of discoveries that could transform our understanding of reality itself, guided by the patient accumulation of evidence and the persistent human drive to understand our place in the cosmic order. The dark matter mystery represents more than just a scientific challenge. It's a reminder that we live in a universe of infinite depth and complexity, where the most profound truths often lie hidden in the spaces between the stars. Lie hidden in the spaces between the stars. The mystery of dark matter has become our generation's greatest scientific quest, a journey that has taken us from the familiar realm of visible galaxies to the edge of comprehensible reality itself. As we stand here tonight, surrounded by this invisible ocean of cosmic matter, we're confronting a truth that would have been unimaginable to previous generations of astronomers and physicists. Every measurement we make, every observation we record, every theoretical calculation we perform points to the same inescapable conclusion. The universe is not what it appears to be. The stars twinkling in your night sky, the galaxies spiraling through the cosmic dark, the very atoms that make up your body. All of this represents less than 5% of everything that exists. We are minority participants in a cosmos dominated by something we cannot see, cannot touch, cannot directly detect. This realization has transformed our understanding of what it means to study the universe. Traditional astronomy relied on light, on electromagnetic radiation, carrying information across vast distances to tell us about distant objects and cosmic processes. But dark matter operates in a realm beyond light, beyond electromagnetic interaction, in a shadow universe that overlaps our own, yet remains largely invisible to our most sophisticated instruments. The implications ripple outward in ways that touch every aspect of our cosmic understanding. Dark matter isn't just an abstract component in theoretical models or a footnote in cosmology textbooks. It's the invisible architect that has shaped every structure we see in the night sky. The Milky Way galaxy containing our solar system exists because dark matter provided the gravitational scaffolding around which ordinary matter could condense and organize itself. Think about this for a moment. The formation of our sun, the creation of the planetary disk from which Earth emerged, the chemical evolution that made complex molecules possible, the gravitational stability that allowed life to develop over billions of years, all of this depended on dark matter's invisible influence. We are quite literally children of the dark universe, our existence made possible by processes we're only beginning to understand. This perspective transforms the search for dark matter from an academic exercise into something profoundly personal. We're not studying some distant phenomenon that has no bearing on our daily lives. We're investigating the hidden foundations of our own existence, the invisible forces that made our universe, our galaxy, our world, and ultimately ourselves possible. The technological quest to detect dark matter has pushed human ingenuity into entirely new territories of precision and sensitivity. In underground laboratories shielded from cosmic interference, researchers have created conditions more sterile than anything found in nature, more isolated than the depths of interstellar space. Their detectors can register energy deposits smaller than the warmth generated by a single bacterial cell, vibrations fainter than the sound of a butterfly landing on a flower petal. Yet despite decades of increasingly sophisticated searches, dark matter continues to evade direct detection. This elusiveness has forced scientists to become philosophical about the nature of knowledge itself. We're learning that some aspects of reality might be fundamentally beyond our ability to study directly, yet absolutely essential for understanding how the universe works. Consider the profound challenge this presents to our scientific worldview. We've built our understanding of the cosmos on the foundation of observation and measurement. We point telescopes at distant objects. We analyze the light they emit. We conduct experiments in controlled laboratory conditions. But dark matter exists in a realm where these traditional approaches reach their limits. We're like inhabitants of a two-dimensional world trying to understand three-dimensional objects that pass through our plane of existence. We can see their shadows, trace their effects, map their influence on the things we can observe directly. But the objects themselves remain forever beyond our direct comprehension, existing in dimensions we cannot perceive. This limitation has led to remarkable innovations in indirect detection methods. Scientists have learned to read the gravitational signatures that dark matter leaves throughout the cosmos, like cosmic fingerprints. They analyze the way light bends around invisible masses, study the patterns of cosmic microwave background radiation, trace the orbits of galaxies within massive clusters. Each observation adds another piece to a puzzle whose complete picture might forever elude us. The theoretical landscape of dark matter research has expanded into realms that challenge our most basic assumptions about the nature of matter and energy. Physicists now contemplate particles so exotic that they barely interact with anything, including themselves. They consider forms of matter that might exist in higher dimensions, leaking gravitational effects into our three-dimensional world, like shadows cast by objects we cannot see. Some theories propose that dark matter might undergo its own chemical reactions, forming complex structures invisible to our instruments. Dark atoms combining into dark molecules, dark matter stars burning dark fuel, perhaps even dark matter planets harboring forms of organization we cannot imagine. An entire shadow chemistry might be playing out around us, as rich and complex as our own visible universe. Other possibilities venture even further into the exotic. Perhaps dark matter exists in a state of quantum superposition across cosmic scales, manifesting its gravitational effects through probability waves that span entire galaxies. Perhaps it represents the boundary between our universe and parallel realities, a cosmic membrane that separates different domains of existence while allowing gravity to pass between them. The philosophical implications of these possibilities stretch our conception of reality to its breaking point. We might be living in just one layer of a multidimensional cosmic structure, with entire universes of dark phenomena operating invisibly around us. The very notion of what exists and what doesn't might be far more complex than our everyday experience suggests. Yet even as we grapple with these exotic theoretical possibilities, the practical search for dark matter continues with renewed determination. New generations of underground detectors push toward ever greater levels of sensitivity. Space-based observatories map dark matter's distribution across the cosmos with unprecedented precision. Particle accelerators probe higher energies, searching for any sign of dark matter creation in their collision chambers. Each approach brings its own unique perspective to the mystery. Direct detection experiments hope to catch dark matter particles interacting with ordinary matter, providing definitive proof of their existence. Indirect searches look for the products of dark matter annihilation or decay, scanning the skies for gamma rays or other particles that might be produced when dark matter destroys itself. Collider experiments attempt to recreate the conditions present when dark matter was first formed in the early universe. The international collaboration required for these efforts has created a global community of researchers united by their shared fascination with the invisible universe. Scientists from different countries, different cultures, different theoretical traditions work together, sharing data and insights in pursuit of understanding that transcends any national or institutional boundary. This cooperation represents something beautiful about human nature when confronted with profound mystery. Rather than retreat into ignorance or despair, we respond with increased creativity and determination. We build more sensitive instruments, develop more sophisticated theories, devise more ingenious experiments. We refuse to accept the limitations of our current understanding. The search has also generated remarkable technological innovations that benefit society in unexpected ways. The ultra-pure materials required for dark matter detectors have led to advances in manufacturing processes used in electronics and medicine. The sophisticated data analysis techniques developed to search for rare particle interactions have applications in medical imaging, environmental monitoring, and financial modeling. The computational challenges of simulating cosmic evolution have driven advances in high-performance computing that enhance climate science, drug discovery, and artificial intelligence research. The precision required for gravitational wave detection has led to innovations in laser technology that improve our ability to measure incredibly small distances and detect subtle vibrations. These technological spillovers remind us that fundamental research, even when focused on seemingly abstract questions, often produces practical benefits that were impossible to anticipate. The quest to understand dark matter isn't just about satisfying scientific curiosity, but about pushing the boundaries of human capability in ways that ultimately benefit all of civilization. As we contemplate the magnitude of the dark matter mystery, we're reminded that science is ultimately about more than just accumulating facts or developing technologies. It's about expanding our conception of what's possible, challenging our assumptions about the nature of reality, and pushing against the boundaries of human understanding. The dark matter enigma embodies all of these aspects of scientific inquiry. It forces us to confront the limits of our observational capabilities, while inspiring us to transcend those limits through creativity and persistence. It challenges our theoretical frameworks while opening new avenues of investigation that we never could have imagined. Most importantly, it reminds us that we are part of something far grander and more mysterious than our everyday experience suggests. The invisible matter streaming through your body at this very moment connects you to cosmic processes that span the entire history of the universe, from the first moments after the Big Bang to the formation of the cosmic web that shapes everything we observe today. You are not separate from the dark matter mystery, but an intimate participant in its unfolding. Every breath you take occurs within a gravitational field shaped by invisible matter. Every heartbeat happens in space, permeated by particles that carry the momentum of cosmic evolution. You are embedded within the very phenomenon we're trying to understand, part of the cosmic web that dark matter has spent billions of years constructing. This perspective transforms our relationship with the universe from that of detached observers to engaged participants in an ongoing cosmic story. We're not just studying distant phenomena, but exploring the hidden foundations of our own existence. Understanding dark matter means understanding the invisible architecture that made complexity, consciousness, and life itself possible in our universe. The quest continues in laboratories and observatories around the world, where dedicated researchers work tirelessly to illuminate the cosmic dark. Each null result teaches us something valuable about what dark matter is not, gradually constraining the theoretical possibilities. Each new observation adds another piece to the magnificent puzzle of cosmic evolution. We may never solve the dark matter mystery completely. We may never develop instruments sensitive enough to detect these elusive particles directly. We may never fully comprehend the nature of the invisible majority that surrounds us. But in the attempt itself, in the persistent effort to understand what lies beyond our direct experience, we discover something essential about what it means to be conscious beings in an incomprehensibly vast and mysterious universe. The dark matter flowing around you right now carries the entire history of cosmic evolution, connecting you to the deepest processes that have shaped reality since the beginning of time. In contemplating its mystery, you're joining a quest for understanding that represents the highest expression of human curiosity and wonder. A journey that continues to reveal new depths of beauty and complexity in the cosmos we call home. And so we reach the end of our journey through the invisible universe, though in many ways we're only at the beginning of humanity's greatest cosmic detective story. Tonight, we've traveled from the spinning edges of distant galaxies to the deepest underground laboratories on Earth, from the first puzzling observations of Vera Rubin to the cutting-edge theories that push the boundaries of physics itself. We've discovered that the universe is not what it appears to be. The stars you see twinkling above, the galaxies spiraling through space, even the atoms that make up your very being, all represent less than 5% of everything that exists. The rest remains hidden in cosmic shadow, shaping reality through invisible hands, holding the architecture of existence together through forces we're only beginning to understand. Dark matter isn't just some abstract concept floating in the void of theoretical physics. It's the invisible scaffolding that made your existence possible. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of your DNA, all were forged in stars that formed within dark matter's gravitational embrace. You are quite literally a child of the invisible universe. As you rest here tonight, billions of dark matter particles are streaming through your body at incredible speeds, carrying with them the entire history of cosmic evolution. They connect you to processes that span billions of years and countless light years of space, linking you intimately to the cosmic web that shapes everything we observe. The mystery continues in laboratories buried deep beneath mountains, in observatories scanning the cosmic web, in the minds of theorists pushing the boundaries of human imagination. Each day brings new possibilities, new ways of thinking about the invisible majority that surrounds us. We stand at the threshold of discoveries that could transform our understanding of reality itself. Whether we ever solve the dark matter puzzle completely or not, the journey itself has already revealed something profound about our place in the cosmos. We are not separate observers studying the universe from the outside, but intimate participants in its ongoing story of mystery and wonder. Sweet dreams, fellow travelers in the cosmic dark.